was the same.
Okay.
And unfortunately, he gave the wrong number for some, but it was because in geometric point of view it is extremely difficult. But if you consider, he tried to establish this number for this P group Z2 to K. But then that it is not. So there is a third method which is almost nothing in now. This MG invariant is very mysterious invariant and in my opinion is very difficult to calculate. So there is I think the end my story about classification. How many time I have still?
10 minutes.
10 minutes? Okay, so it is the beginning of my talk. Unfortunately, but I have slides, so I have now. So the next step in my talk, it is a very, very difficult problem, boundary problem. Everyone knows it was proved in 1982 that every compact Riemannian flat manifold bounds a compact manifold. That means that and it was later was proved by Hamilton and Reuter in 82. So, and then consider an example. If you take hyperbolic manifold with one cusp, as is here, if you cut the cusp, the boundary is a flat manifold. And the question is, if we take flat manifolds of dimension n, is there some hyperbolic manifolds with one cusp, such if we cut this cusp, we get exactly this flat manifold?
Excuse me, what about Klein bottle?
Klein bottle.
It has dimension oriented.
There's no oriented there.
Gieseking manifold. Do you know the three-dimensional Gieseking manifold?
But what about the theorem?
What about? Where is?
Compact, flat?
Yes.
What is it bound?
Which one? This?
Do you need orientation in the theorem?
Here? No, I think it is not necessary. This is not any flat Riemannian bonds compact. It is grouped by just the action of finite group.
And what about the Klein bottle?
Yes.
What?
My question is, what about Klein bottle? How it corresponds to the theorem? It is flat, Riemannian, compact.
Yes, and Klein bottle is not boundary of any.
It's non-oriented.
No. But for example, there is example of three-dimensional hyperbolic manifold of finite volume, which fundamental group of Gieseking manifold. And if you cut this on the boundary, you obtain the, maybe not compact, but you obtain the manifold with boundary with Klein bottle.
The manifold itself may be non-compact.
Yes, manifolds. No, but I think if you cut, because Gieseking has one cusp, Gieseking manifold. So Gieseking manifold has a cusp. When cusp is product of Klein bottle plus infinity, there is a cusp. So if you cut the cusp, so you get manifold with boundary. Non-oriented, probably. It is non-oriented manifold. No, but we are interested in higher dimension. And here it is. And it is open problem. And in 2000, Long and Reed proved that they proved the following. If we have the hyperbolic manifolds with one cusp of dimension 4n, if the flat manifolds of dimension 4n minus 1 has geometric realization, so that there is realization of they have realization as a cusp of some manifold, then eta invariant or signature operator of this flat manifolds has to be integer. And an integer number. easy consequence of Atiyah-Patton-Ising theorem. They were very lucky because the Atiyah-Patton-Ising formula, you can, in this case, you can calculate that this eta invariant has to be integer number, and they also are very lucky because there exist 2 or 3 three-dimensional flat manifolds where this eta invariant is not integer number. That means that they have not realization as a Cusp realization of this three-dimensional flat manifolds. And they use their formula for calculation of this eta invariant given by Volker Neumann student, where it's possible to calculate this eta invariant. And I try to calculate this eta invariant, and I use Donnelly methods. He proposed some formula, but it only works for flat manifold with cyclic homology. And that is, and we check this up to dimension 7 because it is in dimension 7, and for all cyclic because we don't prove for all cases, but each cases we calculate it was always integer. But there are people from Argentina, from Cordoba, Miatello and her students, which gives the new methods of calculation of eta invariant, and they find in dimension 7 flat manifold which is not which eta infinite to eta invariant is not an integer. And the last, I have 5 minutes for the last topics. They are spin structure. I spent the other definition. I think everyone here knows the definition of the spin group and the spin. So, and in what is which I use definition of, if we take classification space, fundamental group of flat manifolds, oriented. We are, because we assume now that there is oriented, and fundamental group on classification space of oriented orthogonal group. So we have here B spin. So existence of spin structure means that this, because we have the classification space. So there is, and I consider vector bundle self-classification space in topological way. So that means that the tangent bundle of flat manifolds with fundamental group gamma is you can up to vector bundle over spin manifolds. That means that this diagram, you can make this diagram commutate, but even if you reduce this to this case. So that there is the very easy criterion for existing of, so on flat manifolds there exists spin structure if this holonomy representation here to SON, not holonomy, the reduction to, because gamma here is the subgroup of SON, semi-direct of, this is the map on the finite group, so that means that flat manifolds has a spin structure if this representation defined by, from definition of gamma, Weber group, you can and this is classical map, covering map from SN to spin, so that there exists homomorphism where this diagram commutates.
What's a Hanschen group? Hanschen.
Yeah, so there is generalization of three-dimensional. I have no time to. If the Hanschen group is very is the following group. Hunter-Band group, it is oriented, any oriented flat manifold of dimension n with holonomy group equal to Z2 to n minus 1. So there is the Hunter-Band manifold, very interesting class for example, this class of manifolds, they are rational homology sphere.
Yes, but you got not manifold but group.
The special case of this
Holonomy group,
guy.
and you get a manifold. Yes.
So
Yeah, and
there is a definition, general definition of oriented Hunter-Band group. It is fundamental group of this manifold. So there is or in other way there is there is torsion-free extension of and with oriented there is the torsion-free extension where this group belongs to oriented. That means that this group belongs to
that's central.
rotation group belongs to this one. So there is the definition. And in 97 they proved that they are not. And here is the sketch. And then we calculate with support of computer Olski structure in dimension 4, 5, and 6. And you have here the number of manifolds. You have orientable flat manifolds, and there is the number of spin structures. So there is statistic of flat manifolds without, because existing spin structure is equivalent to existing of the second Stiefel-Whitney class is trivial. So there is also here.
Nice way to say.
So there is, I think there is